good evening, everyone. Thank you for joining this last in our current series of webinars on technology, near-infrared spectroscopy, and our MicroNIR product line. The topic this morning is our recently introduced products for hazardous locations, safe in the presence of flammable gases, vapors, dusts, and fibers. We're very excited about these products as they open up new opportunities for us. This is the recent series. I don't know if you can all hear my cat in the background. He's helping me out here. These our prior webinars are available by recording on YouTube at the links seen here, and you'll be able to find them after today's presentation as well. Presenting today will be Emiliano and Christina, who have been our hosts for the previous webinars. I'm doing a quick introduction here, and we will also have Paulo Corvo talking about the particulars of hazardous locations, and David Keshela talking about his experience with talking about technology for mills. Right, and there's our agenda for today. So let me begin with a little bit about VAVI. I think we covered this in more detail in previous webinars, so I'll cover it very quickly. VAVI is an American corporation of roughly $1 billion turnover, 2 business units. Our business unit is optical security and performance products, and our focus is on precision optics components and instruments for many different markets. MicroNIR is a product that has been with optical security and performance for about 8 years now. And it's really built on a vision of a smarter world. Our instruments are small, portable, repeatable, reliable, and they're built on the vision that you see here in this slide. Miniaturization. I'll talk a little bit about the technology in a moment, but the unique VAVI technology allows these instruments to be very compact and lightweight. Affordability, by comparison with benchtop instruments and many of our competitors, we offer high performance at a price significantly lower than the premium in the marketplace, without any compromise in performance. Here at the bottom, our instruments are very high performing and comparable with other instruments on the market. And then connectivity. The first instruments were connected by USB, and we now have instruments, the MicroNIR On-Site W and the MicroNIR PAT-Ux that are wireless, connected either by Bluetooth in the case of the handheld or Wi-Fi in the case of the process instrument. The other 2 instruments here are connected by USB. So this is our vision for the future of bringing laboratory performance instruments to the handheld and process markets. I'll talk a little bit about the technology that goes into our MicroNIR instruments. The core of all our instruments is linear variable filter technology. An LVF is a narrow bandpass filter where the bandpass wavelength varies with position on the filter, as you can see here. The basic technology was developed for NASA, for the American Space Agency, for use on interplanetary spacecraft. The advantage being that an LVF makes a very compact, lightweight spectrometer with no moving parts. And that's important to NASA because moving parts are a source of failure. And when a spacecraft is on its way to some remote region, there is a service call is not possible. So right now, there is a VAVI linear variable filter array on the OSIRIS-REx mission, this satellite which is on its way to an asteroid named Bennu, where it's going to pick up a sample of the asteroid and bring it back to the Earth in the year 2023. The principle of a linear variable filter based spectrometer is shown in the upper right here. And let's look at the lower right. Light reflected off of the sample goes through the linear variable filter, which is mated to a linear detector array, so that each detector pixel in this array reads out a different wavelength of reflected light, and that eventually reads out a signal to the computer, which represents the reflected spectrum of the sample. The entire system is illustrated up here on the right with integrated light sources, very long-lived vacuum tungsten lamps, collection optics that gather the light up, homogenize it, and present it to the linear variable filter. And then the instrument has, of course, included electronics, and in the case of the on-site W, a battery and communication back to the computer. There are no moving parts, no free space optics, nothing to become misaligned or wear over time. The units are very repeatable so that chemometric models developed on one instrument can be used on another, and no lasers and no fiber optics. With that introduction, we'll turn our attention to Paulo, I believe, who will talk more about hazardous locations and will lead into the new products. Thank you.
Okay. So nice to meet you all. Welcome to this webinar. My name is Paulo Corbo. I am a manager in a company called Silex Engineering. And my purpose today is to introduce you all with some specific topics related to MicroNIR PAT-Wx suitable for explosion protection equipment. In case you have any questions, any additional question to report to me or to VAVI, you can contact us directly. What's the aim of my speech? I want to introduce you all with some certification schemes which are worldwide spread and mainly based on the territories you can see on this map. In case we extend to the next sheet, we can see the main certification scheme you can face during your activities. We have two main blocks which are concentrated, one in the United States and North America, Canada, and one in Europe, which is called CE Marking European Directives. We have also additional schemes which are following day by day the structure of our two main schemes, which are the EAC in Russia, Kazakhstan and Kyrgyzstan, CCC in China, in Metro in Brazil, and Australian standard, New Zealand standard conformity in Australia and New Zealand. So today we will focus mainly on American schemes, North American and Canada schemes, and European schemes. In case you are approaching to explosion protection certification schemes, you shall refer to specific naming which are reported in this slide, and you can see very often in America ADS-log certified equipment are named against NFPA 70 and specifically to NEC 500 and NEC 505. What are they? They are specific articles, clauses in the NFPA 70, which is an installation standard, which are referring to classified area where we can face the possibility to ignite explosion atmospheres, mainly released by gases or dusts. In case you are approaching North America, Canada, you will see CC, which is the Canadian Electrical Code, and Annex J and Section J 18 are addressing to the specific topics of explosion protection. In case you are approaching Europe, you will hear of ATEX directive, which are regulating all the explosion protection stuff and materials, and are of course regulating the selection, installation and design processes for this kind of materials. You can find in this slide also the remaining schemes, which are EC and TRCU 12 for Russia, CCCX for China, which is quite new and entering in force in October 2020. Metro Portaria 179 in Brazil, and one which is one of the most investigated and interesting schemes, which is the worldwide ICX, fought 20 years ago to encompass the various schemes you can find worldwide, and to give an international approach to the qualification of product intended to be adopted in hazardous location. It is mainly valid so far in Australia and New Zealand, recognized everywhere but not accepted, not directly accepted in spite of the local regulation. So that means if you have an ICX certification, you can access directly Australia and New Zealand, encompassing Australian standard, New Zealand standard conformity. But in case you want to approach Europe or America, then you shall convert this ICX certificate to a local certification scheme. So this is the ICX, it's a voluntary scheme, and you can approach to ICX approaching to their website, and then you will see it's regulated by operational documents. Let's go to the European approach. European approach, which is the ATEX based approach, is regulated by laws. A European directive is a European law, so everything is necessary to qualify a next product is mandatory in Europe. So it's coming out from the European Commission as a European directive, which is a law. How does it work? It works in this way. Either in United States, America, or Europe, you shall always follow every size path, which in the first step obliges you to classify the area. Classifying the area give you the possibility to establish how much quantity of gases or dust can be released by the containment system, and then some qualified area will be characterized by the probability of presence of flammable atmospheres in the air. United States have two styles. They say with the first style called NEC 500 approach, they say you can face two possible probabilities, then two possible areas called Division 1 and Division 2. Division 1 is the most relevant and most dangerous area because you can face releases of flammable atmospheres from, let's say, normal operating condition up to frequently or permanently releases. Okay, so this is a very high dangerous area. Division 2, on the opposite, is less dangerous, and it's only phased when you approach area where the containment system can release the flammables, only in case of accidental rupture or breakdown of the containment system. Going to the approach which is very common in Europe and also common, but not so much as division in United States, you can face the 505 approach or -10-1 approach, which is called zone style classification. Zone style classification is based on 3 types of zones: zone 0, zone 1, zone 2. Zone 0 is the most onerous because just like division 1, you can face releases of flammables very often, frequently, or for long periods up to continuously. Zone 1 is an intermediate area which is based on less frequent releases, but anyway with an appreciable frequency, which lead this area to an intermediate danger. Zone 2 is the less onerous, and you can face a Zone 2 only when the containment system can release flammables for a very short period. We say in Europe that up to 10 hours of releases can create a Zone 2. Up to 1,000 of releases can lead to Zone 1. Over 1,000 hours releases can lead to Zone 0. Okay, so this classification can bring you to understand which is the danger associated with different Hazardous area classification. When the zone classification is known, you can decide for the correct equipment to be installed in the zone. Standards, directive, norms lead you to the correct selection. Nevertheless, in Zone 0, only Category 1 equipment are admitted. So what does it mean? When you have a very high probability of presence of flammables, then you need a very low probability of igniting it. So it's called Category 1. In Zone 1, you can enter with a Category 1 or with a specifically designed equipment called Category 2 equipment. You have an intermediate probability of ignite because you have an intermediate probability of presence of flammables. In Zone 2, which is the lower area, you can enter either with Category 1 or Category 2, or with a very specific equipment called Category 3, which is the equipment specifically suited for Zone 2. The probability of igniting of a Category 3 is higher than a Category 2, which is higher than a Category 1. We have a further classification, which leads to an international approach called EPLs. EPLs means Equipment Protection Levels. They call GA or GB or GG something which is suitable respectively for Zone 0, GA, Zone 1, GB, Zone 2, GC. In case you have flammables as dust, then you will get GA for Zone 20, Zone DB, APL DB for Zone 21, APL DC for Zone 22. That means that Categories 1 equates GA, Category 2 equates GB, Category 3 equates GG, and the same for the dust classification. So you shall only remember Category 1, APL A in Zone 0, Category 2, APL B in Zone 1, Category 3, APL C in Zone 2, and for dust, Zone 20, Zone 21, Zone 22. How can we face flammables and try to not ignite them? we shall act on the concept of ignition of flammables, which is based on 3 components. You need for an explosion flammables in a form of gas, vapor, or mist, or powder, dust, energy to ignite them, but also we need the comburant agent, so we need the oxygen. In case you are capable to separate these 3, let's say, reagents, then you can create a method of protection. You can also admit they can mix down, and then you will create a method of protection by containment of explosion. Or in case you can admit the mix of this agent, but you can limit the energy to ignite the mix of flammables or comburant agent. Anything you do will fall in one of the 22 methods of protection today known worldwide, which limit the risk of ignition. We will see something today when you have a look to an ATEX equipment, so an ICX certified equipment, or an ATEX certified equipment, or an NAC 500 or 505 certified equipment, you will see you will have a look to very rugged equipment, a very strong equipment, very often based on very high level materials. So in case you have a system capable of contain an explosion, you will see it's called XDB, and you will see its body is a very heavy equipment based on a aluminum alloy or an iron alloy, and it's capable to contain the explosion. So in case you have a look to this kind of enclosure or this kind of enclosure, you must be sure this enclosure is capable to contain explosion. Okay, so you have the mix of oxygen, you have the mix of flammables, and inside the enclosure you can have a spark or an hot surfaces, but the enclosure is capable to contain the explosion, and nothing is spread to the outer flammables. For other equipments like that or like this, you have the capability of the system to work to so low energy that the flammables mix cannot be igniting in any way. So you are talking about intrinsic safety, and then you will see XIA or XID. Okay, so let's have a look to the MicroNIR X version. So it's called MicroNIR PAT-Ux for the X application. You will see the electronics which are elaborating the signal from the sensor are working inside this enclosure, and then nothing can happen, because in case gases are entering this enclosure together with oxygen, and in case they are ignited, the explosion is confined inside. The sensor is working on a different approach. Let's call it XIA, intrinsic safety, energy limiting base. Then nothing happens, because this energy is not capable to ignite the external atmosphere. Many other methods of protection are available, like this. This is based on pressurization, or like this, which is based on isolation inside the electronics. But mainly we want to concentrate on these 2 methods. Okay. Let's see how to proceed. First, you have a standard equipment, and then you have to transformate it to an X equipment. So where you have a standard electronics or a standard enclosure, then you need a specific electronics and a specific enclosure. That's what this is what happened to MicroNIR. They upgrade to an X application. So how do they recognize the possibility to upgrade the MicroNIR to X application? First, they study which kind of gases they can face. If you have a look to the literature, then you will see many different groups are available. when you see group 2C stamped on a label, then you see this equipment is capable to interface hydrogen and acetylene. Or if you see group A, then this is capable to phase hydrogen and acetylene. That means this is the best that human can get, because if you can face this so dangerous gases, then you can face any gases known in this world. In case you see second B or second A, only a part of the gases can be phased. Groups in second B are higher igniting energy than second C, and second A has a higher igniting energy than second B. So it means that an equipment market for second A is suitable only for second A gases. An equipment suitable market so for second B is suitable for second B and second A, but not for second C. In case you see second C, it's suitable for any gas. The same applies for the United States qualification. A is suitable for any gas, B only for BCD, C only for CD, D only for D. Okay, this is the equivalent marking for dust, which has the same identical concept, only Setur 3C means metal dust or carbonaceous dust. Non-conductive dust are qualified 3B, which are less dangerous than 3C, and fibers and flyings are classified 3A, which are less dangerous than 3B and less dense than 3C. But the concept is the same as gases. Last but not least, the maximum surface temperature of the equipment. Gases can ignite for contact with hot surfaces. If an hot surface is classified TC or 85 degrees, then it's the coolest temperature we can emit for gases. What does it mean? If an equipment is stamped with T6, it's suitable for all gases known. If an equipment is stamped for T5, it's suitable for T5, T4, T3, T2, T1, but not for gases T6, because gases T6 will ignite when in contact with this equipment. So in case you will find T4 on the label, the equipment is suitable for T4, T3, T2, T1, but not for T6 and T5. In America, we have more detailed scale, but the basic concept is always the same. If you associate the related temperature to the symbol, then you can decide which is the maximum temperature of the equipment and decide if it is suitable for the Hazardous area. Finally, you can have a look to the main styles marking. When you approach the ATEX, which is valid in Europe only, you will see this hexagon. Then the group 2 means this equipment can be used in surface industry, not in mines. In case if you need a mines, you will see a group 1. Category 2 is one of the 3 categories explained before. 2 means this equipment is suitable for zone 1. G stands for gas. In case you have a dust, you will see a dust. Okay, so this equipment is suitable for zone 1 gas. This equipment is suitable for zone 21 dust. I see the same also in the EPL. GB means the same like category. It's suitable for zone 1. DB is APLB for dust, the same for category 2 dust, zone 21. I see T6, this equipment is heating up maximum up to 85 degrees, so it's suitable for any known gases. And second C means that is the best equipment we can realize because it's suitable for any gas. The same applies for the dust. T80 degrees is the best we can do for a dust equipment, and 3C is the best we can do for a dust equipment. Finally, let's have a look to the American marking. American marking is a bit more explicit. You can see this equipment is suitable for class 1. Class 1 means it's suitable for gases. Class 2 means it's suitable for dust. And class 3, it means it's suitable for fibers and flyings. Division 1 means it can go in division 1 and in division 2. Groups A, B, C, D means this equipment is suitable for all known gases. T5 means the maximum surface temperature of this equipment is 100 degrees. It can be adopted everywhere, but not with T6 gases. The additional admitted hazardous area marking according to NEC 505 changes the division in zone, I told you before, and then explicit the method of protection. The second meaning of second C and T5 is exactly the same like in Europe. You recognize it's an American marking because you see this A in front of AX, which is not in the European marking, means it stands for American explosion protection equipment. These two examples report the marking of MicroNIR. This application is for the zone 1, zone 0. This is the label for the IS barrier box, the big aluminum alloy base explosion protected box, which I show you in the I've shown you in the picture before. If I have a look to the ATEX marking, I see 2G, so category 2 gas. It can go to zone 1 and zone 2. The method of protection is explosion protection, and it can interface an equipment based on intrinsic safety that can be installed in zone 0. The IS barrier box itself can be installed in second A, second B, but not in second C, and its maximum surface temperature is 135 degrees. That means most of the gases can be interphased, but not T5 or T6 gases. The APLs at the end replicates the meaning of category 2. It can go in zone 1. This is the marking for the dust. Zone 21, dust tide method of protection. I can interface the intrinsic safety equipment. The intrinsic safety equipment is at the end the spectrometer, which is classified XA. I can interface all the known explosive dust. The maximum surface temperature is 135 degrees. The EPL is suitable for zone 21. The same is expressed in the American marking, so class 1, class 2, gas dust, division 2, or zone 1, zone 21, okay? So finally, the spectrometer, which is intrinsic safety, can go in zone 0 because we have a category 1G, or zone 20 because we have a category 1D. It's indeed a GA, DA. Its method of protection is XIA, so it's based on intrinsic safety. The gases admitted are second A, second B, not second C. The maximum surface temperature is 135. Same is for the dust. The last one, so this is the equipment called PAT-Wx. It's suitable for zone 2 or zone 22 because it's a category 3 gas or category 3D dust, partly based on intrinsic safety, partly based on increased safety. Maximum surface temperature 85 degrees. All gases, all dust are emitted. Everything confirmed by APLs. So that's all from my side. I leave
Thank you, Paolo.
Speech to my colleagues in case.
I appreciate a lot your presentation, and actually it made my life definitely easier because Steve introduced the company. You talk in a very complete way regarding the ATEX certification, And I have a very easy task because I just want to show you a picture of the new product, and afterward I will leave the stage to Cristina and to Davide. Here you have the traditional product that we introduced starting from the 2012. We have IP65 product, we have accessory, we have the software that is 21st CFR Part 11 compliance, and it includes also a chemometric package. But we came across to the fact in the real life that the customer were starting to move from the early adapters that were application in the laboratory, going, thanks to the success of the MicroNIR, into the real process equipment. Here you have some example: fluid bed dryer, air shear mixer, width and floor analysis in the production of mill, explosive manufacturing, sugar content and concentration, in this case using a liquid flow cell. So here you have the picture of the PAT-Ux and of the Wx, and this is exactly something very easy to understand after the Paulo's presentation, where you have in yellow the hazard area with the process equipment, and you see the MicroNIR in the right hand side, that is classical PAT-U, or better, it looks like the classical PAT-U connected to the process equipment, with a USB cable that goes to the intrinsic safety barrier, here the killer box that was mentioned before, and all the two are inside the hazard area, and the computer is outside, and there is a communication using a customer supply conduit where there is inside a Ethernet cable. This is the MicroNIR. As you can see, the PAT-U versus the UX is just a little bit longer in the back. There is a 125 meter of USB cable that goes to the intrinsic safety box, and here you can see that you have, let's say, the connection with the USB, the Ethernet port, that is this one. And this is a function that I really like, the possibility to connect an external trigger like in the PAT-Wx. This is the connection for the 24 VDC power, and this is how the device looks like in terms of certification. I don't want to spend too much time on here, but thanks to the Paulo presentation, you can really try to read this classification by yourself. In the case of the PAT-Ux, that is the device for static application, we have the barrier box that is basically 2-1, the spectrophoto. I simplify, I know that Paulo disagrees on this. The spectrophotometer, it can also go in the 0, but together with the other one, it becomes 1, so it's a 2-1 zone certification. But we learned that the certification is even more complex and consider the gas, consider the superficial temperature, and so on. And this is the other baby, is the PAT-Wx, that is a perfect tools when you have to work in a production environment. You need a wireless device, for example, for a tumble blender. Differently from the PAT-W, the Wx has a little bit bigger battery, is maybe few grams heavier. You can see from the graph here that for the customer that they already the PAT-W, there is not the system, the easy release way to open this one, to open the lid for replacing the battery, but you need a special tools to open in order to avoid to open it inside the hazardous area. You see in the back also that is missed the Ethernet communication and the external trigger, so it's not available for this stuff. It was available for the previous one, and is also a little bit stronger. Our colleague from the R&D, they said that they have to pass a more stringent, it's called a torpedo test, when an object is thrown on the surface and the device should be undestroyed, not destroyed afterward. And but is exactly the brother of the PAT-W for all the other stuff, including the possibility to have the gyroscopic sensor that is dedicated for the PAT for the blending. This is the label. It works a little bit in a let's say less dangerous environment. In fact, this is zone 2.2, as you can see here. Okay, the other one is 2.1. I'm good with the presentation, and really thanks to Steve and to Paulo that made my life very easy today. And I leave the stage to Christina, that she will show implementation on liquid.
Yes, thank you, Emiliano. So regarding liquids, we will focus on the prediction of the API concentration during a chromatographic purification. This work was done in a pharmaceutical company. So this is our experimental setup. You can see that a MicroNIR PAT-Ux was used, and we have also a flux cell produced by NanoSense that has 1 millimeter path length, and it works in transflectance thanks to the stainless surface in which the light can reflect and come back to the sensor. In this process, we have a solution that passes through a basic ion exchange chromatographic column and perform the API purification. The aim of our work was to define the endpoint in which we have maximized the API yield, and we reduce what we call the undesirable byproduct, that are two products that arises at the end of the elution phase. In this case study, we decided to acquire 6 spectra for each hour, so 1 spectrum every 10 minutes, for a total of 50-55 spectra for each elution. They are around 70 or 8 hours of elution, and every hour 1 aliquot of the eluate was analyzed by primary methods. In particular, the concentration of API was measured, and also the concentration of the 2 unwanted byproduct. We decided to work on different elution column and different batches to understand the reliability of our models. First of all, we performed a feasibility study that was done at line, and I'm showing you the final model for the determination of the API concentration. And you can see that with MicroNIR on site, with the side view vial holder accessory, we were able to predict the API content with an error of 4.73 gram per liter in a range that vary between 0 and 100 gram per liter. So we are less than 5% of error with the on-site W equipment in the at-line mode. Then we decided to move and implement our ATEX device directly in the process. And here you can see the evaluation of the process with the principal component analysis. On the left side, you can see the raw spectra on the API, and I have highlighted the region in which this particular molecule is absorbing. So in the right part, you can see the PCA score plot. If we try to follow the evolution timeline, so what is happening inside the chromatographic column, you can start from the rectangle in the right part of the graph, this one. And here you have the first 10 spectrum that we are acquiring, so the first 2 hours of the elution. And this is due to the fact that the column is full of pure solvent. So we take 2 hours for removing the pure solvent from the column. And now, in spectrum number 13, the elution starts. And we can see that the elution moves in this direction. And from spectrum 25 until spectrum 40, we have the maximum elution of the API, the strong changes in our spectra. So we pass from a lower value of PC1 and higher value of PC2 going up. And then we can see that we have another drift of our elution line, and we are not coming back to the pure solvent. Why? Because this drift is due to the creation of byproduct, unwanted byproduct in this process. So what we would like to find is the right moment in which I stop the process with the high-end concentration of API, and I'm able not to produce too much byproduct inside my elution. These are the models that we implemented in process. These are still models that are in development because we are collecting right now some data. But you can see that for these first batches, we were able to obtain the same error that we had with the on-site W, but directly in process, mounting the PAT-Ux equipment directly into the elution, the chromatographic column. And we are around 5% again. I also show you this reference versus predicted value of one of the two interference, the byproduct. So you can see that not only we are able to detect the byproduct, but also to evaluate their concentration. So we can confirm that the MicroNIR PAT-Ux was demonstrated to be able also in process and online to evaluate this liquid sample that contains the API. With this, I think that we can pass to the agro food and feed application.
Yes, Cristina, thank you. Let me introduce.
You already, okay, you are sharing, Davide, thank you.
Yeah, okay. Thanks. Want to say something, Emiliano?
I just want to say thank you for joining us. And I know that we talk a lot regarding pharmaceutical application, but I believe that your application is very interesting, especially for the Industry 4.0 approach and for the artificial intelligence approach. I let you go. Thank you.
Thank you, Emiliano. Thank you all to be here today. I show an application of a near IoT sensor in process industry using artificial intelligence for data processing. This project is done in the Innovation for Meals laboratory, that is an integrated multidisciplinary laboratory specialized in artificial intelligence, process optimization, and energy efficiency. The team is made up of Polytechnic University of Bari, that makes the state of scientific art available. IDEA 75, that is the engineering company that implements the results of research in Industry 4.0 applications for milling sector. And Casilo Group, that is the industry that validates the solution on site, provides the necessary improvement feedbacks, and direct the research and development activities. Okay. So, in recent years, the needs along the value chain of wheat have changed. For each one of the many wheat uses, specific grain quality requirements are preferred. So the possibility to obtain reliable and quick information about kernels quality is constantly becoming more important for all the players of the wheat value chain. So the business needs are the three questions here reported. How many times the inbound outbound logistic is delayed by the availability of quality check of the production batch? During production process management, how often doubtful choices are made due to unavailability of the quality characteristics of the batch? And if you had real-time quality data of batch, wouldn't it be easier and faster to automate processes and operation? As you can see, this question are question of every process industry, so it's not only specific on milling sector. At present, the quality parameters are controlled by the quality by test approach, like operator check or laboratory measurement that you can see on the left and in the middle column. It means that the quality is tested only on representative samples of the final product, with the risk of having products below the desired quality threshold to be expensively reallocated. Moreover, the analysis involved in the determination of rheological parameters are expensive, time-consuming, and require specialized personnel. The solution is achieved by the model quality by design concept, It is based on the ability to monitor the process in real time and accordingly adopting the production process to maximize product quality. This is possible using sensors to measure directly the processed materials. In quality by design, a quality profile is designed and the production process is organized and controlled so to reach the target quality. This is exactly, you can see on the right, the column, and the properties that sensors are able to deliver to this kind of process. And this means that we are talking about the zero defect manufacturing principle. This is the capability to analyze the quality of the final product and to adapt the production process in real time. This is exactly the final objective of Industry 4.0 technologies. So, okay. A very important topic for all equipment suppliers and operators working in milling plant is the dust explosion risk. We talk a lot about this, and the only thing that I would like to share with you is that the first legislative regulation in Germany of explosion protection was released a few years ago when a wet mill in Bremen view a dust explosion when died 14 persons. So dust explosion protection is essential for safety of grain process plant. A lot of machine can be involved in this problem. On the right side, you can see some kind of machine that are present in the milling industry process. The problem is to use instrumentation that is ATEX compliant. So in the context of the quality by design, the PET process analytical technologies are the instrument allowing to evaluate the process performances. The evaluation is obtained with quantitative indicators regarding the improvements introduced by the planned process organization, with the possibility of giving feedback to the control strategy of the process. The instruments used for the analysis of performance of this process are the VAVI sensor PAT-Wx and PAT-Ux. The sensors obviously are ATEX, so they can be installed in the used in explosion hazard environment. VAVI spectroscopic sensors in combination with multivariate data analysis, so-called chemometrics, fits well the application due to rapidity of measurement, non-invasive character, the small size, and the resistance to a harsh production environment like humid conditions, vibrations, and dust presence. These in the figure are the measurement points in the production plant where we installed the sensor to realize the digital traceability along the production. The 4 production stages are with receiving, with conditioning, flour bending, phase, and flour shipping. MicroNIR sensors are interfaced with the milling plant, enabling the prediction of physical, chemical, and rheological characteristics for wheat kernels and flour, both. The challenges of quality by design can be reached by exploiting the Industry 4.0 and the Internet of Things principles. The concept is based on the interconnection among machines, devices, and sensors in the industry. The communication between different components of the industrial process allows sending control rules to the plant on the bottom left, so to adapt the process behavior in real-time, reaching the desired quality profile. The green boxes on the left are the heterogeneous data source that we are collecting. The data flow through connectors like OPCDA, that is the connector that we use for the MicroNIR sensor, you can see in the blue box, and join themselves in the data lake, the yellow box. The gray stage is a processing phase that produces control logics to common plant machines. Moreover, the processing stage reshapes the data. Useful data models are used to let the information to be shown in the dashboard. In this way, people that work on quality, production efficiency, maintenance, and energy efficiency can study time series, statistical indicators, and main events that we evaluate starting from the measurement of the sensor. Before using the sensor in the plant, a phase of testing was carried out. We made a laboratory prototype to simulate the continuous flow of the product in order to test the probe and its operation. In the first picture, you can see the MicroNIR software running on the laptop during the test. After this phase, probes were installed into the plant. In the second picture, you can see in the middle of the conveyor the installed probe. On the left, a window useful to check the load of the conveyor. And on the right, a sampler used to capture the flour samples. Using a specific software, in this case with the partial least squares method, prediction models for physicochemical and rheological parameters have been developed. Looking at the flour diagram in the picture, the way the points are distributed into the charts represent how good the prediction of the parameter will be. This is the job done by the classical chemiometrics algorithms. The raw spectral curves generated by the sensor are transformed in numerical parameter, and they are useful to understand and control the production process. Now we can have a look at the contribution of the artificial intelligence benefit. With the algorithms based on artificial intelligence, it is possible to evaluate a wider range of information. Is still possible to predict the physical, chemical, and rheological parameters with models developed in a different way. So we can have some kind of model review using different kind of algorithm to generate the model. Or is it possible to directly classify the product? As you can see in the bottom left image, the different colors are an automatic classification of the product, measuring the characteristic from the NIR raw data. We use the artificial intelligence to develop an algorithm for automatic data validation. This is not about the prediction model. If you put a raw spectral curve in any model, regardless how good or bad it is, it will get a parameter prediction. In this case, the validation is about how the probe is working on the plant. For example, the algorithm is able to understand and to discard automatically all the measurement done by the probe when it's not completely surrounded by the material. In the bottom right image, you can see the automatic classification of this condition. The red spectra are the good ones, the curves that will produce a correct parameter estimation using the prediction model. The green and the blue spectra are the ones that, still using a good prediction model, will lead to a wrong parameter value estimation. Generally speaking, the artificial intelligence can do some things like extrapolate information on plant operation, forecast production and performance, optimize plant resources to gain energy efficiency, and calculate key performance indicators difficult to estimate with classical analysis and modeling methods. In this picture, you can see another functionality implemented using the VAVI sensor and related with anomaly detection. The production monitoring that is in the image is realized with little blue circles, one circle per probe reading. And this circle are the output of a machine learning algorithm that estimates the production flow rate. The red dots are the output of the tracking system of production cycle status on/off of the plant. An error in the tracking system is automatically detected comparing its output with the one of the flow rate estimation algorithm. As you can see on the right in the yellow box, there is a different condition compared to the one on the left, and you can see that the red line and the blue circle are in the same side of the graph. A different condition, as I say, from the left. So this is a way you can use the VAVI sensor and an algorithm to estimate a plant condition and check an anomaly detection automatically. This is a comparison chart between analysis done by the laboratory, the quality by test method, classic, and the online parameters prediction done by the near-infrared sensors. Using a near-infrared sensor is an investment with a short payback time. In fact, the cost of a probe is similar to 1 year of operating cost of laboratory personnel and consumables for analysis done using the traditional quality by test approach. But to be more precise, the chart shows some peculiarities of one solution compared to the other one.